In this video, I'm going to discuss solving exponential equations. Now, before we jump into some examples, we're going to look at this first question here to get the general idea of what we're looking for. So it asks us which equation is true. Does 4 to the third equal 4 squared? Does 5 to the third power equal 5 to the third power? Or does 3 to the third equal 7 to the third? Well, hopefully we can quickly see that it's the one in the middle that's correct. 5 to the third, which is 125, equals 5 to the third, which is 125. Why? Because 5 to the third is 5 to the third. They're exactly the same thing. But the reason why I'm asking this question is because I want to emphasize one in particular thing that's going to be useful when we start looking at the equations. What I want you to see is that in order for these two exponential expressions to be equal, their bases have to be the same and the exponents have to be the same. If we look at the two examples on the outside, notice the first one. The bases are the same, but does the exponent of 3 equal the exponent of 2? No. So this one's not true because the exponents aren't the same. If I look at this one, the exponents are the same, but the bases are different, so that's not true. Okay? So in order to be equal, we need the bases the same and we need the exponents the same. All right, let's go ahead and look at some examples now that we have that idea down. So if I look at number 1, notice my bases are the same. I have 4 to the x equals 4 to the fifth. Well, if I want these two expressions to be the same, and I know the bases are the same, well, what should I know about the exponents? They must also be the same. So I can just drop the exponents down, and I know the x, this exponent, must equal the other exponent. So in this case, x must be 5. Okay? Notice if I checked my work, if I plugged in a 5, does 4 to the fifth equal 4 to the fifth? Yeah, so it checks out. All right, let's look at some tougher examples. Number 2 here, I have 3 to the x minus 4 equals 3 to the 6th power. Once again, my bases are the same. So I know if the bases are the same, in order for these two expressions to be equal, the exponents must also be equal. So I can just drop them down and set them equal. X minus 4, this exponent, must equal the exponent on the other side. I add 4, and I get x equals 10. Now, once again, I can check my work by just simply plugging 10 back into the equation. If I plug 10 back in, 10 minus 4 is 6. 3 to the 6th power equals 3 to the 6th power. All right, let's look at some trickier ones when the bases aren't the same. So looking at number 3 here, notice in number 3, I have 4 to the x power equals 2 to the x minus 5. Notice the bases here are not the same. Okay, so in a problem where the bases aren't the same, our first goal is to make them the same, to rewrite it so that the bases are the same. So how can I rewrite 4 so that it has a power of 2? Well, I know 4 is the same thing as 2 squared. So I can replace the 4, get rid of it, and rewrite it as 2 to the second power because 2 to the second power is 4. I need to keep the exponent of x on it because if I had 4 to the x, then this needs to have an x on it, and then that will equal 2 to the x minus 5. Now, once I have this rewritten, I have to use my exponent rules. We have a rule that says when I raise a power to a power, I can simplify by multiplying the exponents. Or in other words, I can take x and I can multiply it to the 2. Well, if I take 2 times x, I'm going to get 2 to the 2x equals 2 to the x minus 5. Okay? Notice all of this work I've done so far had one goal in mind. I wanted to get the bases the same. Why did I want to get the bases the same? Because I knew once I had these bases to be the same, okay, they're both a 2 now, I know that in order for this expression to be equal to this expression, the exponents must also be the same. So now, once the bases are the same, I can just drop the exponents down and set them equal to one another. 2x must equal x minus 5 in order for these two expressions to be the same. Well, when I solve this, I have minus x, I get x equals negative 5. Once again, I can check my work by plugging in the negative 5 if I wanted to. All right, let's look at one last example here, number 4. So here, once again, the bases aren't the same. Okay, I have an 8 and I have a 4. Now, I need to figure out what base goes both into 8 and 4. And I can use a power table to help me here. So I know I'm dealing with 8 and I know I'm dealing with 4, and I see that they have a common base of 2. So I can rewrite the 8 as 2 to the third power, right? 2 to the third power gives me 8, and that's taken to the 2x. And then I can rewrite 4 just like I did in the last problem as 2 squared with x minus 1 on it. Now, just as before, when I raise a power to a power, I can multiply the exponents. So 2x times 3 is 6x. And then likewise here, when I raise a power to a power, I can multiply. However, I'm raising it to a binomial, meaning I have two terms on the outside as an exponent. So when I multiply these, it has to work like distribution. This is going to get distributed out to both things. So first I'm going to keep my base of 2. 2 times x is 2x. 2 times negative 1 is negative 2. Okay? And once again, just to reiterate, this first part, my whole goal is to rewrite the bases and then simplify the exponents so that the bases are the same. Because I know once the bases are the same, in order for this thing to equal this thing, the exponents must be the same. So 6x must equal 2x minus 2. Okay, I can then minus 2x from both sides. I'll get 4x equals negative 2. Divide by 4, and I'll get x equals negative 1/2.